Okay, so our last major topic before we put all this together into some circuit analysis is electrical resistance. So electrical resistance is a measure of how difficult it is for electric current to travel through a material. So some materials have a high resistance. They don't allow current to go very easily. We call those insulators, so plastics, rubber, wood, those types of things. Other materials have a low resistance and they allow electrical currents through more easily, and generally metals, and we call those conductors. We've already talked a little bit about those. Now normally I would do a voltage current demo here, but I think we're going to skip that and just go straight to sort of the results, mostly for interest in time. So our connection between voltage and current. So if you imagine you turn up the voltage, you keep adding batteries together, and you start getting a larger voltage, 6 volts, 12 volts, 18, 24 volts. It isn't that difficult to see that that would push more current through a wire. Okay, so if we were to do that in a organized fashion and collect that data, we would actually get this type of relationship. Okay, so voltage is proportional. That's what that little fishy sign means. Voltage is proportional to current. So as you increase the voltage, you increase the current. If you were to collect that data, you would see this is a direct variation. So going way back to grade 9, which means it passes through the origin right down here. So we have a nice simple equation of this form, y equals mx. Okay, so you can see that over here, and what we would find is the slope of this line, okay, is our resistance. Okay, and that would be a gauge of how difficult it is for the current to pass through the wire. Now, what's really good or nice about a direct variation is that you could take any two pairs of information, and if you divided them, you would get the slope of that line. Okay, and that's the nice thing about a direct variation. So we're going to take advantage of that in the very near future. Now, all of that put together creates something called Ohm's law, and this is the last piece we really need. So V equals IR, or you could rearrange it, resistance equals voltage over current. Okay, an ohm is measured, resistance is measured in ohms. It's 1 volt per amp. Okay, and if you have any sort of nerdliness, you'll understand this quote. Resistance is futile. No, it's not. It's voltage divided by current. Aha, aha, aha. Okay, so let's throw one last piece on here. From the grade 11 Ontario curriculum, you need V equals IR, and everything we do in this course will be at a constant temperature. When the temperature is allowed to vary, then Ohm's law breaks down a little bit. IB folk, you need to know this. So you have ohmic and non-ohmic behavior. So we just looked at this one right here. So a metal at a constant temperature, you'll notice they've plotted it a little bit differently, but you'll notice it plots as a straight line. If you have something like a filament lamp or a diode where the temperature of the object is allowed to change, that changes the properties of that material, and it could either increase or decrease the resistance. Okay, so that's an important distinction to have. And I'm going to, in the interest of time, ask you to read a little bit of this. So just pause it and read it because it's all there. And I want to try and keep the video length short because we do have quite a few slides to go through today. So this piece right here, ohmic, what you need to understand, ohmic will be straight lined, non-ohmic will be curved lined, and it's all based on whether this temperature remains constant. Okay, so if you need to, pause it and scan the rest. So here's a worked example. The graph shows the applied voltage V versus the resulting current I through a tungsten filament lamp. So that's an old school lamp. Okay, find R when I is 0.5 milliamps and 1.5 milliamps. Is this filament ohmic or non-ohmic? Well, right away we should see that this is non-ohmic because it has a curved relationship. So that's the first piece. But the part that's really interesting is if you draw little lines up from 0.5 and take them over, okay, to find the voltage on this left-hand side, and you do the same with 1.5. When you do that division, you come up with two very different resistances. So at the second value over here, you actually have increased almost 2.5 times the 0.5 resistance. So as this problem, as you start having more current go through this problem, it gets warmer, okay, and the resistance of the filament lamp actually increases. And that would be an example of a non-ohmic. Okay, so now electrical losses. Everything has resistance. We tend to model some things as being resistance free. We don't usually account for resistance in the wires of a circuit. It just becomes a bit tedious. But something called a superconductor, okay, is a substance that has almost zero resistance. We don't have a lot of them available to us because normally they need to be really, really cold. So something like minus 100 Celsius. And then they become super effective at allowing electrical current to pass without losses. It's just not viable for us to do something. But however, if we had a resistance-free electrical grid, that would save a great deal because we lose a great deal of electrical energy in transmission alone. So if you send, say you send 100 joules through a very long electrical power transmission line from a hydro dam that's several hundred kilometers away, you may only get 40 joules of usable energy. Okay, so that's the type of thing we're talking about, and the rest would go out to heating the wires, those types of things, and losses. So that level of efficiency can depend on distance, the machinery involved, etc. But that's something to keep in mind, that the efficiency of our power lines is also a factor in our electrical consumption. Okay, so now resistance. There's a couple ways to model this, and again, a lot of these slides speak for themselves, so I'm not going to go into them too in depth. But this is a really good analogy. If you want to think of resistance this way, if you have a milkshake and you have a very long straw and a very short straw, you would understand very quickly that it takes a lot more effort to drink a milkshake through a very long straw. Okay, and so there is a proportional relationship between the resistance and the length of the wire or the length of the straw. The other one you can test is even if you kept the length of straws the same, but you change the diameter of the straw or the cross-sectional area, as you make the straws larger in diameter, it becomes easier, okay, to be able to drink that milkshake. So that is an inverse relationship. So take a moment, think about that. You have experience with that, I'm sure, trying different straws. If you want to, make yourself a milkshake, go try one. And you can have a hands-on resistance demonstration right in your house. Okay, so resistance is also based on what the materials involved are. So we've talked about conductors and insulators, but not all conductors behave the same way. Okay, so this is definitely an IB specific concept. This is called resistivity. Okay, so the resistivity depends on the materials. Okay, so there's a little expression down here. Okay, and this little row, this little symbol here is the resistivity of a material. You would have to be given that. You don't have to discover that. But it's a relationship that ties in the length, the area, cross-sectional area, and the actual resistivity of the material involved. Okay, so that's a little relationship that ties those pieces together. So you would have to be given something like this. So you can see the resistivity of these different metals. Okay, that would go into that little row in that previous equation. You'd need to know the cross-sectional diameter of the wire, which would lead to your cross-sectional area, and you'd need to know the length. And then you can calculate what the resistance of that wire would be. Okay, so it looks something like this. Note that resistance depends on temperature, so we're not going to be exploring that. We're going to leave that out for now. But what is the resistance of a 0.00200 meter long carbon core resistor having a core diameter of a very small number? Assume the temperature is 20 degrees Celsius. So we have a length, we have an area, okay, and we can look up our resistivity from the table, just like that. And when we put all that together, we can say that this little resistor is 9.17 ohms in resistance. Not a super complicated calculation, it's just multiplication and division. It's more knowing what those pieces are and how they link together. Okay, so this is what it looks like. If you've ever seen resistors before, normally we would again play with these in class. So if you cut one open, you'll see they have a little carbon center. Okay, and they're milled around, mechanically milled to have either more carbon or less carbon. Okay, so the less carbon there is, the harder it is for the current to flow. Okay, and the more carbon it is, the easier it is to flow. So as you control that amount of carbon, you get to control how much resistance that little resistor adds to the circuit. Okay. Different type of resistors, and again, a lot of this is IB specific, but so I'll let you read some of it. There's wire wound resistors. Boy, that's tricky to say. We have variable resistors or potentiometers. They have little dials on them that you can twist and turn, so you can change from, say, 10 ohms to 1,000 ohms, so you could have some flexibility in what those resistors do. You have thermistors, which are temperature dependent. You have light dependent resistors, and again, all of these are mostly IB specific, but they're kind of interesting to know that they're out there. Their properties change when they're exposed to either heat or light. Okay, so different types of resistors have different schematic symbols. So this one here might also look like this in the Nelson textbook. Potentiometers, you'll notice there's a little arrow on here, and you could, again, most of the stuff you can look up. It's provided. You don't have to memorize this, but it's good to know that, hey, that arrow through the resistor means something. I should go look it up. Okay, different types of resistors. Here's your thermistors, your light dependent resistors. Okay, let's see if this one here we can actually do something with, because we can use this one. Oh, my text all jumped around here. Let's give me a second to modify my text, because come on, computer, catch up. So what we do have on all of these little resistors is a color code. Okay, and let's see, we'll get that up there. And we'll move these guys down. All right, so the little color code that's on them, they all have specific resistance, so let me just slide this up. And again, you don't have to memorize this, although there's a bunch of shortened acronyms or things out there for doing that. Each one of these little colors is tied to a number. So the first digit 1, second digit 0 for this one, and this tells you the number of zeros. The last one, you'll notice there's slight spacing here, is the tolerance, so it'll tell you whether it's plus or minus 1, 2, 5, or 10%. The more sophisticated and important your electrical equipment is, the more you would want to have smaller tolerances. Okay, so if you follow this one, this would be 1.0 times 10 to the fourth, and there you are, 100,000 ohms, plus or minus 10%. Okay, and again, you don't have to memorize any of that. That would always be provided. You should kind of get an idea on how to read it. That would be a useful skill. All right, so let's do a quick calculation. Calculate the resistance of a load with a voltage of 25 volts and a current of 410 milliamps. So right away, that bothers me, okay? Because I need to know, when I use my expression, I need to know that's V is in volts and I is in amps. That's really, really important. So this here would become 0.410 amps. Okay, so that would be the first thing I'd want to catch. And now if I go to solve for my resistance, I would have my 25 volts on top, my 0.410 on the bottom, and if I punch that in my trusty calculator, I get basically 60 ohms or 61 ohms because it's a resistance. Okay, so again, the mathematics part is not that difficult. It's just some multiplication and division. So if you want to pause it here, try these two questions, and then I'll reveal the answers. Okay, so let's have a quick look. First one, what is the resistance of a toaster element? So V equals IR is how I always remember them. I don't memorize both forms. I know voltage is 120. Current is 6.5, so I'm solving for R. So I'm just going to divide both sides by 6.5 and 18.5-ish. And that is measured in ohms. So 18 ohms. Okay, what is the resistance of a car starter with a 450 amps of current and a voltage of 12 volts? Okay, remember we talked about half an amp being enough to stop your heart. So here's a car starter, okay, producing 450 amps. So things it's important to understand. Okay, so what is the resistance? Go straight to the formula. So resistance is 12 over 450, and then 12 divided by 450, 0.026, oops, lost the 2 there, ohms. Okay, oops, 27, so I was pretty close. Again, the calculation not particularly difficult, just making sure you put things in the right location. Okay, so now we're going to take that definition of resistance, we're going to combine it with our previous power discussion of power equals voltage times current, and we're going to come up with two new formulas. Okay, so if we take these power expressions, and again this is mostly a reading question, so if you isolate the IR part, substitute in for V, this is a new expression, power, oops, better turn to a pen. Oops, that's the wrong one. Not an R. P. My goodness. P equals I squared times R, or you can isolate the I and substitute it in and get another variation. So if you have a formula sheet handy, this is a good one to have. You can add, for electricity, you can have 3 different versions of the power expression that utilize velocity, voltage, current, and resistance in different ways. So put that somewhere on your formula sheet. That's good to have. Okay, so the graph shows the VI characteristics of a tungsten filament lamp. What is the power consumption? Okay, so it asks for power. It's at 0.5 and at 1.5. Okay, so now if we go back to our expressions here, we have V and I. Okay, so we can use those. So as we substitute in, we can calculate that the power, as the resistance increases, we already talked about this filament lamp, this one has a higher resistance, it uses up more power or more energy per second than this one right here. And that should make sense. Okay, so an ohm meter, we haven't done much of this, but an ohm meter is a device used to measure electrical resistance. Ohm meters are connected in parallel and must never be used on a circuit that's live. So what that means, if the circuit's running, you do not stick an ohm meter on there. You wait till it's turned off and then you can put that on there and take a measure, and they're done like voltmeters where they're done in parallel. Okay, so we'll finish off section 11.7, 1 to 4 and 12. If you could try those, that would be awesome. Thanks for tuning in.